Hello everyone, I'm Norman Wildberger. Today in this series on famous math problems, we're going to look at one of the most interesting and baffling conundrums of modern times. A problem called Newcomb's paradox. This was described for the first time by the prominent American philosopher Robert Nozick. In 1969 he wrote a paper called Newcomb's Problem and Two Principles of Choice, in which he outlined this problem or paradox that had been enunciated a few years earlier by William Newcomb, who was a physicist and described this problem and studied it in 1960. The whole issue was popularized and made very famous by Martin Gardner, the very well-known popularizer of mathematics, who wrote about it in his mathematical games column in Scientific American in 1974. And it turned out to be one of his most influential columns, generating huge amounts of debate and discussion at that time. And even today, this paradox is still a very interesting thing. It has not really been resolved. Many different people have gone in different directions and said different things about it. So in this lecture, what we're going to do is we're going to describe the paradox, first of all, and then we're going to settle the mystery, at least mostly. So I'm going to give you something of a little bit of a new point of view towards this paradox that will allow you to understand it in a completely clear and mathematical way. So there'll be something new even for those of you who are very familiar with the paradox. So I'd like to read to you a little bit from Martin Gardner's article, Newcomb's Paradox, which appeared in Scientific American. It's in this compilation of some of his works, The Colossal Book of Mathematics by Martin Gardner. It's a highly recommended book. So Newcomb's Paradox, and he begins this way. One of the perennial problems of philosophy is how to explain or explain away the nature of free will. If the concept is explicated within a framework of determinism, the will ceases to be free in any commonly understood sense, and it is hard to see how fatalism can be avoided. Why work hard for a better future for yourself or for others if what you do must always be what you do? And how can you blame anyone for anything if he could not have done otherwise? On the other hand, attempts to explicate will in a framework of indeterminism seem equally futile. If an action is not caused by the previous states of oneself and the world, it is hard to see how to keep the action from being haphazard. The notion that decisions are made by some kind of randomizer in the mind does not provide much support for what is meant by free will either. And then a little bit later he says, well, what has free will to do with mathematical games? The answer is that in recent decades, philosophers of science have been wrestling with a variety of queer prediction paradoxes related to the problem of will. Some of them are best regarded as a game situation. One draws a payoff matrix and tries to determine the player's best strategy, only to find oneself trapped in a maze of bewildering ambiguities about time and causality. All right, so that's sort of his introduction, part of his introduction to this paradox of Newcomb. Let's start with a preliminary problem. We have a room in which there's a table, and on the table there are two empty boxes. There's a little box and a big box. To start off with, there is nothing in either box. Now an oracle, and this oracle could perhaps be a wizard, or might be an alien, might be a very fancy computer, or it might be an angel, or some other mysterious kind of being, offers to play a game with you. All right, he's going to do one of two things. He's going to either put $1,000 in the little box and $0 in the big one, or he's going to put $1,000 in the little one and $1 million in the big one. He's going to do one of those two things. So you can see that no matter which choice he takes, there will always be $1,000 in the little box, and there's either going to be 0 or $1 million in the big box. After he's done that and put the money in there, you're going to have a choice. And your choice is A, to take the money in the big box, or, well, you might think that I'm going to say take the money in the little box, but that's not the choice. The second choice is to take the money in both boxes. All right, so your first choice, choice A, is to take just whatever's in the big box, which could be either 0 or a million, or you can take the money that's in both boxes, which will either be a total of 1,000 or a total of 1,000,001. And the question is, what are you going to do? Now that's a relatively easy problem. I think most of you will agree. If you spend a few minutes thinking about it, I think we'll all agree that why would you not take the money in both boxes? Obviously, that's the sensible thing to do. It's clearly superior to option A. Just make sure that you convince yourself that you understand this problem and that you're probably inclined to take option B. So Newcomb's problem is exactly the same as the previous problem with some additional information included. I am now going to tell you a little bit more than I told you on the previous slide. I'm now going to tell you how the oracle decides whether to put 0 or $1 million in that big box. Okay, so the oracle makes a prediction before he chooses. He's going to look into your mind, and if he thinks that you will be modest and choose just the big box, then he's going to reward you by putting $1 million in it. On the other hand, if he predicts that you are going to be greedy and you're going to choose both boxes, then he's going to punish you by putting $0 in that big box. The little box, we've already agreed, always gets $1,000 no matter what. And now, famous math problem number 7, which is Newcomb's paradox. The question is, what are you going to do now, given this additional information about how the oracle decides? Do you choose the modest option A, or do you choose the greedy option B? This problem is a difficult one. It involves a lot of different aspects and points of view and different ways of thinking about things, and I'm going to assign it a difficulty 8 to 10. It's not entirely clear that the problem is well posed. It's not entirely clear that it has a solution. And it's certainly clear that a lot of people have already spent quite a lot of time thinking about it. So it's an unsolved problem as far as we're concerned, and it's a rather difficult unsolved problem which ultimately might be related to a whole bunch of naughty things about quantum physics and the large-scale structure of the universe. Maybe. Now there's a relevant fact that you need to know. Okay? This oracle is not just an ordinary person. This oracle is very good at predicting. So the oracle is almost always right in his predictions so far. So you can imagine that this oracle has played this game with quite a few people already. Perhaps he's already played it with you several times. And in all of those cases, or perhaps in the vast majority of them, it's turned out that his predictions have been right. We don't know how he does it. It might be luck. It might be that he's making huge calculations in his mind, or it might be that he has divine connections. For whatever reason, this oracle seems to be effective in predicting, very effective in predicting, and that's an important, relevant fact that you better take into consideration when you're choosing. So, what are you going to do? Are you going to choose just the big box, or are you going to choose both boxes? One amusing aspect of this problem is that most people, when they hear of it the first time, are almost immediately certain that they know what the right answer is. It's almost obvious to them what the right solution is, what choice they ought to make. The curious thing is that the population in general is roughly divided equally about what the obvious choice really is. The problem is that there's two very good arguments in both different directions. All right, so let's have a look at, first of all, the argument for A, for being modest and just choosing the big box. Okay, so here's the argument for that. So we argue as follows, that if you choose A, the oracle will most likely have predicted this, because the oracle is good at predicting. And so he will have put $1 million in that big box, and you are going to get $1 million because you're going to be picking that big box. On the other hand, if you choose B, the oracle will most likely have predicted that too, because the oracle is good at predicting. And because you've chosen B, he has decided to put $0 in that big box. And so therefore, you're going to take the contents of both boxes, and you're only going to get $1,000. So if you choose A, you're almost certainly going to get $1 million. If you choose option B, taking both boxes, you're almost certainly going to get $1,000. So obviously, you should choose A. Any rational being can see that this is the obvious logical choice. So here is the argument for B, for the choice B, where you're taking both boxes. I think you have to agree it's also somewhat compelling. It's sometimes called the dominance argument. So the argument is that the oracle has made his decision. Whatever he has decided, and the money is now in the boxes. Maybe there are some judges for the game who have witnessed this. Okay? People have seen the oracle put the money in the boxes lids are closed, the oracle has left the room, now you're entering. Okay, so if the big box has $0 in it, you are better off to choose both boxes, because you're going to get $1,000 in that case instead of 0. On the other hand, if the big box has $1 million in it, you are better off choosing both boxes, because then you're going to get $1 million and $1,000 instead of just $1 million. Either way, no matter what is in the boxes, you are better off choosing both boxes. So B is the obvious choice. Any rational being obviously is going to choose option B. This lovely problem, paradox, has generated a lot of discussion over the years. People from my generation who are mathematicians many of them have seen this problem, because we used to read Martin Gardner's articles in Scientific American almost religiously. They were uniformly brilliant and interesting articles. Now, these days, maybe young people are not that familiar with Martin Gardner's work. If you are such a person, you are encouraged to look up Martin Gardner's work and try to get as many of his articles as you can and read them. But a lot of us will have seen this problem. If you have not seen this problem before, it's great to think about it and argue over it with your friends. The debate naturally touches on many areas. Free will is involved, determinism, there's ethical and psychological aspects to it, there's economic theory involved, there's probability, there's it's all modern physics, quantum mechanics as well. So there's lots of different takes on it. There's also quite a few variants of the problem. For example, there's a variant where you are in fact allowed to look in the boxes before you choose. It's kind of a new game. You can decide whether you want to look in the boxes and base your decision on that. There's another variant where instead of having the money in the boxes, and the boxes are closed, because maybe that makes you think that somehow your choice is changing the amount of money. What the oracle can do is leave a number in the second box, a large number, say a natural number, and if that number is prime, then you're going to get $1 million, and if the number is composite, you're going to get 0. So you can actually look in the room and you can see the $1,000 in the little box, and you see this number in the second box, and it's already there, and then you have to decide. And it's only later that you can compute that that number is prime or not. So that version of the problem makes it completely clear that the oracle cannot change his mind depending on what you choose. This topic has also made some people argue that maybe free will is an illusion. There are many possible directions that people have gone in arguing about this topic. The paradox itself seems in some sense vaguely posed because of the strange role of the oracle. What kind of an object creature is this actually? And the natural question is it possible to reformulate this problem completely clearly and mathematically without any philosophical or quantum mechanical aspects? And if so, is there then an unambiguous answer? And I'm going to try to convince you that the answer to both these questions is yes. That it is possible to formulate the problem completely clearly, and that then, yes, there is an unambiguous answer. So as usual in mathematics, when we're a little bit confused or unclear, it's good to try to concentrate on the definitions of things and what exactly are the quantities that are appearing here. So in this problem, I think it really helps to identify some implicit quantities that are in the problem that we can make explicit. There are actually some numbers associated to this situation, and once we become aware of what those numbers are, it helps us in formulating and understanding what the problem really is. So prominent amongst those is the ratio between the big box payout and the little box payout. Okay, so these numbers, 1,000,000 and 1,000, actually play quite a role in the problem. If you change these numbers dramatically, then the nature or the answer of the problem, at least, will change for many people. So if you reconsider the problem, for example, where that 1,000,000 is replaced with 2,000, then a lot of people who may be leaning towards option A might drift towards option B. Okay? So the ratio between these two numbers is an important feature of the problem, and it's useful to identify it explicitly. And let's do that. Let's call it K. Now, in terms of the oracle and what the oracle is actually doing, I think there is really two probabilities associated to the oracle that encapsulates the power of the oracle. And I'm going to call them PA and PB. So P sub A is the probability that the oracle guesses your choice if your choice is A. So what I mean by that is, suppose that you play this game with the oracle many, many times, and sometimes you guess A and sometimes you guess B. And you keep a record of how many times the oracle was right. Okay? So let's then count the number of times the oracle was right when you guessed A, and divide by the total number of those events. You're going to obtain the probability, or an estimate of the probability, that the oracle is right, guesses your choice correctly, when your choice is A. On the other hand, there's another number, P sub B, which is the probability that the oracle guesses your choice correctly if your choice is B. And it's important to realize that these numbers don't have to be the same. The oracle could be better at predicting your guess if your guess is A rather than B, or the other way around. Now, if you were playing this game with anything other than a wizard or an oracle or some divine creature, then these numbers would typically be 1/2. If you played a lot of times and sometimes you guessed A and sometimes you guessed B, and you kept a record of how many times the person guessed, chances are that probability is going to converge to 1/2. It's going to be very hard to be anything other than 1/2 in the long term. But we may assume that this oracle has very special properties. And that assumption is built into these probabilities. These probabilities being different from 1/2 is encoding mathematically the assumption that that oracle has the properties or the predictive abilities that we're supposing he does. Then there's another number that features, which is the little box payout. The amount of money in the little box, let's call that M, which in the original problem is $1,000. All right, now we have some quantities to work with, and we can be a little bit more mathematical. So what we're going to need in addition to this is just a little bit of familiarity with expected values and basic probability theory. All right, so in the theory of probability, there's a very important notion of expected value, which allows you to estimate how much value there is in a situation that has some various outcomes, typically money, associated with various probabilities. All right, so let's just understand this in a simple case. Suppose that we have two possible outcomes of some situation yielding payoffs of N1 and N2. You can think of these as dollars, with probabilities P1 and P2 respectively. So you're going to get payout N1 with probability P1, and you're going to get payout N2 with probability P2. Then this quantity here, P1 times N1 plus P2 times N2, is the expected value. In other words, if you play this game many, many times, exactly the same game many, many times, and you keep a track of how much money you're making, sometimes less, sometimes more, and take an average of the amount of money that you're getting per game, then this is the number that you're going to obtain. So you can think of that's what the meaning of expected value is. It's a long-term average of how much you should expect per game if you play the game repeatedly. For example, a very simple example, suppose that you have a 1/10 chance at winning $400. In this case, there's only one event, the possibility of winning $400, and its associated probability is 1/10. The expected value for that is what you get by multiplying the probability by the payout, which is $40. So on average, you're going to get $40 if you play this game many times. Most of the time you're going to get 0. Every so often you're going to get 400. On the average, you're going to get $40. $40 is the expected value for this game. So if you wanted to play this game, say in a casino, it would be reasonable to pay $40 or roughly $40 to play this game once. A slightly more sophisticated example, suppose that someone offers you the following game. You're going to roll a dice, get one of the numbers from 1 to 6. And if you get a 1, 3, or 5, you're going to get a prize of $100. And if you roll a 2 or a 4, you're going to get a prize of $1,000. And if you roll a 6, bad luck, you're not going to get anything. So how much is that game worth? Well, it's an expected value computation. The probability of getting 1, 3, or 5 is a half, because there's 3 out of the 6 possible outcomes that will give you this result. So 1/2 is the probability for 100 multiplied by the value of 100. The probability of getting 1,000 is 1/3, because 2 out of the 6 numbers give you that result. So the probability of 1/3 times the payout of 1,000. And we add those two together, which would be $50 plus $333.33, for a total expected value of $383.33. If you play this game many, many times, this is the expected value that you should be able to get per game. So on average, you're going to make $383.33. Although sometimes you're going to make more and sometimes you're going to make less. This is a very fundamental formula for computing how much a game is worth. So let's have a look at this Newcomb's paradox game with this viewpoint of expected value. And we're going to look at the generalized Newcomb problem, where instead of having $1,000, we have M dollars in that little box. And instead of having 0 or a million, we have 0 or K times M. So K is just some multiple of M. Could be 1,000 or something different. And we have these two probabilities, P sub A and P sub B. These are the probabilities of the oracle being right if you choose A or choose B. All right, so let's compute now the expected value of choosing A. I remind you, A is the option where you just take the contents of the big box. So if you just take the contents of the big box, how much can you expect to get? Well, it depends what the oracle has done. It depends whether the oracle has guessed right or not about your choice. So the probability that the oracle has guessed right when you've chosen A is P sub A. So in that case, the probability P sub A has to be multiplied by the expected value of what you would get if he guessed right. If he guessed right, it means he's going to put k times m in there, and that's going to be your payout, because you're going to take the contents of just the big box. So the probability times the payout. Of course, there's another possibility. There's the possibility that the oracle is wrong. That's 1 minus p sub a. If the oracle is wrong, it means that when you choose that box, there's going to be $0 in it. Painful. So the payout then is 0, but it's still part of the formula. So the total expected value for the A option is, just this first term, p sub a times k times m. If you play the game many, many times, then the expected value you get when you choose A is going to be this amount of dollars. Okay, what if you choose B? That means you're going to choose both boxes. The probability that the oracle has guessed that already is what we're calling p sub b. So the oracle might be right, in which case that's p sub b, or he might have been wrong. That's 1 minus p sub b. If he's right, how much are you going to get? So if he guessed right, he guessed that you were going to choose both boxes, that means that he's put $0 in there. You're going to get a total of m dollars in that case. So there's the probability times the outcome for that possibility. The other possibility is that the oracle is wrong. So there's the probability that the oracle is wrong. And here's the payout in that case. So if the oracle is wrong, he put km in there, and you're going to score the big jackpot. You're going to get m plus km. So the probability of the oracle being wrong times the payout that you get if the oracle is wrong. Okay, so let's expand this. There's going to be an m plus a km, so that's m times k plus 1. There's this pb times m. That's going to cancel with this pb times m. And then there's going to be one more term, minus pb times km. So altogether, the expected value is m times k plus 1 minus p sub b times k times m. All right, now the question that we're interested in is, when is the expected value of A bigger than or equal to the expected value of B? In other words, under what circumstances is it better to choose option A rather than option B? All right, so the question is, when is this thing bigger than or equal to this thing? Well, it's a relatively simple inequality. We have this as the left-hand side, this is the right-hand side. Let's take this term with the minus sign over to the left-hand side. Then the left-hand side will be p sub a plus p sub b times km. And then that'll be bigger than or equal to what's left over here, k plus 1 times m. And we can simplify this because we can divide by the m. It turns out that the m is irrelevant. All right, well, so we divide by m, and we divide both sides by k to get the condition that p sub a plus p sub b is bigger than or equal to 1 plus 1 over k. And this formula, as far as I'm concerned, solves Newcomb's paradox. It's telling you what to do. It's telling you that if the probability of p sub a plus the probability of p sub b is bigger than or equal to 1 plus 1 over k, where k is the multiple between the big possible payout in the big box and the little payout, then you should choose A. So for example, if k happens to be 1,000, which is our original problem, then this is the number 1 plus 1,000, so it's just a little bit more than 1. Then if the combined sum of the two probabilities is just a little bit bigger than 1 and 1,000ths, then you should choose A. So in other words, if you believe that the oracle has some reasonable probability of being right, pretty small, right? This doesn't have to be a lot bigger than 1. If the oracle is just guessing by random, then we expect both of these numbers to be half and this total to be 1. So if the oracle is just a little bit better than random, for example, maybe the oracle is your mother or your husband or wife or best friend, and they happen to know you and the way you think, then my guess would be you might very well choose A, because there's a good chance that these probabilities add up to something bigger than 1. Unless perhaps you've conspired to make your choice hard for your mother or wife or husband or best friend. Perhaps you're flipping a coin secretly to make your decision. In that case, you're pretty confident that your best friend still only has a 1/2 choice. Okay? So if you're flipping a coin and your best friend is guessing, you're still better off choosing B. On the other hand, if K is something like 2, so if we have a much smaller jackpot, 1,000 and 2,000, then this number is a total of 1.5. And then we would require a fairly big probability total here to convince us to just choose the big box. So you'd have to believe that this oracle was very, very effective in predicting your choice in order to just take the big box. So with this formulation, what we've done is we've put the philosophy and the metaphysics aside. We've encoded all that metaphysics in these probabilities. These are the probabilities that you assess the oracle as having. Okay, so if you believe the oracle's probabilities are p sub A and p sub B, and you can calculate that however you like, and that might involve any kind of religious or philosophical thoughts you might have. But once you've calculated or conjectured or estimated what these things are, then this formula will allow you to decide whether to choose A or to choose B. Alright, so that's my take on Newcomb's paradox. I'm sure that many of you will disagree and there will be counter-arguments, and that's the nature of this paradox. It's a lovely generator of discussion. So the philosophical or metaphysical aspects of this are interesting. The connections with quantum mechanics and free will are enticing, and I think those topics are very interesting in modern physics, because modern physics is so strange and complicated, really. Mathematics is so much simpler. Alright, so on our next famous math problem, we're going to go to Leonhard Euler, who is my favorite mathematician of modern times and the overriding genius of the modern age. And we're going to look at one of the many problems that he generated, problem of how many ways are there of subdividing a polygon into triangles. That was a problem that he posed to his friend Goldbach in a letter. That's what we're going to do next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.